Hi guys, today's lecture is about adaptive control. Previously we have learned cascade, feed forward, split range, inferential, ratio controller. So with respect to that, we have one more controller which is adaptive controller. So generally what is adaptive? So adaptive is called a control system which can adjust its parameters automatically in such a way as to compensate variations in the process characteristics. So this is how your adaptive control is. So adaptive control is also a control system. So which can adjust its parameters. Suppose if there is a change in the process, if there is any change in the process characteristics. So adaptive controller means in this adaptive controller, you have to introduce one mechanism so that if there is any change in the process, this mechanism will come into play and it will adjust the parameters automatically so as to compensate the process characteristic variation. So this is called as the basic methodology of adaptive controller. But why do we need adaptive controller in the chemical processes? There are two reasons. One reason is most of the chemical processes are non-linear. For example, I'm not going to take any non-linear process, but let me take one simple spring. Okay, so the spring, it has only certain this elasticity. Okay, for example, I can I can keep a weight, for example, some 2 kg. So if I keep more than 2 kg, it will lose its elasticity. So which means if the weight is up to 2 kg, this works like a linear system. If you increase more than 2, then it behaves like a non-linear. So this logic is applicable to all system, even for a human nature also. So until and unless if he is subjected to any issue, then only we'll understand his linear range and non-linear range. Any person, if you keep on disturbing only for 1 or 2 minutes, he'll be okay. But if you disturb more than that, definitely he'll behave like a non-linear person. So likewise, every system has its threshold. Only if you can operate within the threshold, it works linearly. If it is beyond the threshold, then it becomes non-linear. Okay, so we are going to apply that. So non-linear means we can't predict how it works. So that's why we have to introduce one mechanism to compensate those non-linearities. Okay, so that is called as adaptive control. So why do we need adaptive control in the chemical process? One thing is most of the chemical processes are non-linear because the linearized model that we have designed can be applicable only for a particular range of a particular steady state. If that desired steady state operation of the process change, if you change that threshold point, the best values of the controller parameters will also change because we have designed a controller only for linear controller. So for example, for a linear controller, suppose if you take PID controller, so KP you have taken as 4, KI is 4.8, 4.8, and KD is zero point 0.8. Okay, so this is how you have checked it and you have tuned it, and this is applicable for linear parameters. But say for example, if the process characteristics changes, which makes the system non-linear. So if the system becomes non-linear, then this controller values is of no use. Okay, so in that case, we have to give a mechanism that will adapt for these changes. So that's what here, I mean, the linearized models that are okay for particular range. If that desired range varies, then the best value of the control parameters will also change. So this implies there is a need for controller adaptation. So there is a need for controller adaptation when the linear process changes to non-linear process, then these controller parameters is of no value for this. So in that case, we need a mechanism called as controller adaptation because that it has to adapt to the change. So for this reason, we are going for adaptive control. That is number one. And the second reason is most of the chemical processes are non-stationary. So we have to agree this because chemical process is a complex process. Non-stationary means the characteristics change with time. Okay, for example, you can take this heat exchanger. Okay, so just this is a tube actually. Okay, in this you pass a water, hot water, and then in the outside also you are going to supply steam. So this is steam, and then this is hot water. Okay, after few days, what happens is, because all the water is salty, when you keep on boiling, so you will have some deposits. You will have some deposits. Because of the deposits, the heat transfer coefficient will be very poor because of this deposits. Okay, so in this case we can say this is non-stationary process, so this is called as fouling. So fouling has to be, so that is why in industry what they do is they do during shutdown they just remove this fouling deposit, and so that the heat transfer will be efficient. So this is also one example for non-stationary. So most of the chemical processes are non-stationary because the characteristics changes with time. This is change with time means initially it there won't be fouling, but after 10 days or 1 month you'll have a deposit of that salt water, which is called as fouling. So we mean the process is not stationary because the characteristics are changing because of the falling. So non-stationary means the characteristics change with time. For example, the decay of the catalytic activity in a reactor decreases the overall heat transfer coefficient in the heat exchanger due to fouling. Okay, this is one example. And then this change leads again, so because of this change the performances will be deteriorated. So that is why we have to go for controller. So controller adaptation is needed again. Okay. For these two reasons, we are taking the help of adaptive controller, which is called as adaptive mechanism. One is non-linear process, another one is non-stationary process. Okay. So how do we do that? What is the objective of adaptation procedure? So for this, first we have to determine the objective function. Okay. So objective functions in the sense we know that 1 by quarter decay ratio. Okay, so we have to adjust because yeah, we know that this is non-linear and non-stationary. So we are introducing some adaptation mechanism, but how long you are going to change or how long you can make the mechanism to adapt, how long? So there is a limit. So for that we have to fix the limit. Like your process should behave in 1 by quarter decay ratio, or your integral ISE. ISE is equivalent to E square. Okay, E square dt. So this value should be of some zero point 0.4 or 0.06. Likewise, you fix the value for ISE, or you can take this gain margin or phase margin, some value. Okay, so like this, you have to create an objective function. That objective function should satisfy either 1 by decay ratio of the output, or the ISE should be this much value, or the gain margin should have this much value. So this is how you are going for an adaptive mechanism. So what is the need for it? Because we need objective function. What is the role of objective function? This objective function will guide the adaptation mechanism to the best adjustment of controller parameters. So you have to adjust the controller parameters, that is the best adjustment, in such a way that this criteria will be satisfied. So this is called as objective function. Okay. Then what are the two different mechanisms for the adaptive control? One is programmed. Okay, programmed or scheduled. Programmed or scheduled adaptive control. This is one mechanism. This is the first method. And then second methodology is gain scheduling. Gain scheduling adaptive. So these are the two mechanisms. So we'll see how it works. Okay. So first we'll see this. So this is programmed. So this concept is programmed or scheduling adaptive control. So this is programmed or scheduling adaptive control. So let's see how it works. Okay, so this is the normal inner loop is a normal feedback process. Say for example, this process is a non-stationary, or this process is a non-linear process which introduces some different characteristics in the process. Okay, so what we do is we have to take the auxiliary variable. So measure that auxiliary variable. Then that auxiliary variable is put under adjustment mechanism. Then once the auxiliary variable is under mechanism, then we have the new controller values. Give those new controller values, then that is taken into control. Then if you apply that controller parameters to the process, then whatever nonlinearity it introduces, that will be managed. So this is how it works. So let me explain this with one example. This is one ratio controller. This is normal ratio controller. So how it works, we have to take this is FA, and already we have discussed some ratio, and then this FA into 3 by 2 should be equivalent to this one. So you have to change the controller until this flow rate will be equivalent to this. Say for example, this process is non-stationary, so you will not be able to achieve this FA into 3 by 2 because of the non-stationary or non-linear process. So what we do is, instead of measuring the flow rate, take a temperature, take the temperature of the air. So that is your auxiliary measurement. Okay, because while you take the temperature, because this is fuel to air ratio, so fuel is not under control, so then this is called as wild stream. So air is under control. So instead of measuring the flow rate, because flow rate already we are measuring for this, okay, but we have to take auxiliary measurement, which is not for this controller section. So take one more variable. So measure this. So I'm going to take the measurement of the, I mean, temperature measurement of the air, and then that temperature measurement will be given to the mechanism, and then this mechanism will generate a new ratio. That ratio is added to that. So in that way, the ratio accounted into, and then that is given to a controller. Accordingly, it will adjust the process automatically. This problem will be solved. So this is called as programmed. We have programmed or we have scheduled. So how do you do that? How do we schedule this? We schedule an auxiliary measurement, okay, which is not for this. We take another variable, for example, temperature. Instead of flow rate, take the temperature of there. So we scheduled, we programmed, and then that auxiliary measurements is put it under adjuster mechanism. That is, you have to change, that is, measure this variable, and then here you have some controller values. Change the controller values, I mean, check that values, and keep on changing the values so that it will adapt to that. So you get one new controller parameters. That parameters are added to the controller, then that is given to the process. So this is called as programmed or scheduled adaptive controller. Okay, so in this, the outer loop includes parameter adjustment. Parameter adjustment means here you have some parameters like x1. So you have some, in this adjustment you have some parameters like say x1, and then so x2t or x3t square, like that. So t we cannot change, but we can change x1, x2. Okay, so for that, see here, or we can say this air temperature is T. Okay, this is T. To this adjustment mechanism is added. So keep on tuning the values and get the controller parameters. Then try and check whether that non-linearity will be addressed. If not, again change the value, change this value and this value, and get the new controller parameters. Add to that. Then that is given to a process and check for the addressal of non-linearity. So likewise, you can keep on changing this. So for that, without a goal, we cannot change. So for that, we have to use the objective function, which is ISE or 1 by quarter decay ratio or gain margin or phase margin. So this is how. So this is called as programmed scheduled adaptive controller. Okay. Then the next mechanism is gain scheduling adaptive controller. Okay. So here this method is gain scheduling, because in the previous case the process is well known, mathematical model is also available because we know the model, and then if there we have auxiliary measurement also possible, and then by measuring the value we can schedule or program the adaptation mechanism. That is called as scheduled or programming. So next one is gain. We are concentrating on gain scheduling. So gain scheduling adaptive control. Gain scheduling, it's not AC, it is adaptive control. Gain scheduling, adaptive control. So say for example, one normal feedback controller. So this is the process, and then this is the valve final control element. This is the controller, and then this is the measuring device. Okay. So in this, we can take K overall. K overall means overall constant. So what is overall constant? You take all the gains. First, let's start from process KP and then KM and then KC and then KF. Okay. Say for example, your KF changes. Okay, KF varying. This KF changes. Okay. So we have to calculate the controller parameter. So how do you calculate KC? KC equal to K overall divided by KP, KM, KF. So if your KC changes, automatically your KF changes. Accordingly, your controller parameters will be changing. So you have to devise a new mechanism so that whatever changes that are applicable to this gain, so that has to be taken care of adaptive mechanism. So that is called as gain schedule. We are considering only the gain. So how do we do that? So this is a normal process. So here also we have to take the auxiliary measurement. But here, this is a general process which measures, for example, temperature or flow rate or pressure. This is a process. But apart from these variables, we take another measurement, which is stem position. Yes, you know that this is a control valve. So here is the this is stem, then you have a valve seat. So the stem position is measured, and then that stem position is given to this block, because already we know that Kc equal to constant, this is overall constant divided by this. Okay, why do we take the stem position? Because who is varying in this case? Kf is varying. So Kf is varying. That is why you have to take a variable which is relevant to Kf. So this x is given to you. So this, if you give it to x value to this, automatically this Kf will be addressed. So in that way, and then once it is addressed, then it gives a new Kc values and give that Kc value here. So what we do is, this is a general process. Suppose if there is any issue over here, what we do is, so we take a auxiliary measurement of stem position. The stem position is given to this, and then we know that for the stem position, I mean, input is the stem position and output is the flow rate. So, and then your flow control element, sorry, final control element for a control valve is input is stem position, output is flow rate. So in this case, we can find out the gain. So if S is given to you, automatically this will vary. You can change the value. Then if you change the value, controller value will change. So apply the changed value over here and check whether it is addressed or not. So likewise, you have to adapt. You have to, how do we adapt, or how do we adapt to the changes? By measuring the stem position. So this is called as gain scheduling adaptive control. So there are two scheduling mechanism. One is programmed scheduling mechanism. Another one is gain scheduling mechanism. Okay. And the next one is self-adaptive. So self-adaptive control. So what is self-adaptive control? Okay, what is self-adaptive control? If the process is not known well, okay, so we need to evaluate the objective function online using the controlled output values. So how do we do that? If the process is not known well, so already we know that the system identification, so we know the input, we know the output. So this is known to you, this is known to you. If this is not known to you, so if the process is not known to you, we need to evaluate an objective function using the controlled output values. Then adaptive mechanism will change the control parameters in such a way that to optimize the maximum value of the objective function. So I will explain with an example. So let us take this one. So this is model reference adaptive control. So which is MRAC. Okay. So here the problem is this model is known to us. We don't know the model. So what we do is, we with the set point, when we get one model using system identification method, so we know the model. So give the set point to the model will give the model output. So this output is similar to this process. This is the original process. This is the real-time process. And then this process is under control. Okay, this is a controlled process. So we have to include all these control parameters and make one model. So that is why, how do we make a model? We take this output, take the output, and we know the input. With this input and output, get the model. So using system identification method. So get the model. give that model to this. So now we have to check whether the model you have framed is perfect or not. For that, for the same mod, for the model, give the same input to this, and then this output. So now this is the model output and this is the actual output. So you have to compare this and check the error. Okay, so this error should always be minimum, then only the model is good. Because what is self-adaptive controller? If the process is not known to you, the mechanism has to adapt itself so that it gives you the model. So now the model output is compared with the original output and the error is there, and then the error is given to a mechanism. Again, here the adaptive mechanism is, you have the objective function. That objective function is 1 by 4 decay ratio or ISE, or you can create your own criteria. Accordingly, change the values, and then your control parameters will be changed. KC values will be changed, then give that and check for it. So likewise, still this, because if the error is 0, automatically this problem will be solved. So this is called as model reference adaptive controller. So MRAC. So the next one, so in this, how do you do that? First, the steps to do this is, first make a reference model which tells us how the controlled process output ideally should respond to the command signal. So accordingly, make a model. The model output is compared with the real process output. The difference between two outputs is given to the adaptive mechanism, which is just like a computer because it computes a value. And then how do we do that? And then we give those values so that it will adjust the parameters of the controller in such a way that to reach the objective function. So this is called as model reference adaptive controller. This comes under self-adaptive controller. Okay. So the next one is one more self-adaptive controller is STR. So which is self-tuning. Self-tuning because R for regulator. So self-tuning regulator. So in this case, what we do is, first from the controller, okay, take the input, okay, and then take this process output. Then here you have to estimate the model. In the previous case, we gave the model and then that model is subject to the input and check the output. That output is compared with the real output. But here, to the model itself, directly give the real process output and the real this, then get an estimator, estimate the model, then that estimator is given to a mechanism, then here you change the values, then get the QKC value. So this is called a self-tuning regulator. So it consists of two things. One is this recursive state estimator. What do you mean by recursive? Because you have to keep on re-estimating till you reach the required value. So this is called as recursive. This nature is recursive. Okay, so take the recursive nature of the parameter estimator. This is one such component. Then next component is, obviously we have adjustment mechanism. In this you have objective function. Okay, so this parameter, for example, if this parameter gives the the transfer function is e power minus TDS approximated value. So tau s plus 1. Then what we do is, then using the measured values of the manipulator variable, so from this we know the manipulator variable and we know the controlled variable, this control output. Estimate the values of parameters. So you have to estimate what is KP, what is TD, and what is tau. Estimate these parameters and employ. So how do you estimate the parameters? We have the basic thing is least squares estimate. So you can use that least squares. There are some more regression models. So apply that model and get the parameters. So once the parameters are known to us, then those parameters are given to the adjustment mechanism so that you can adapt for the best values of the control parameters and immediately check those values with the controller, and then the control output is given to the process, and in that way you can manage the changes that occur. Okay, so this is called as self-tuning controller. Okay, self-tuning. So this is self-tuning, or we can say self-tuning regulator. Okay, so far we have seen adaptive controllers. So we have seen why do we need adaptive controller for a chemical process, because of its nature of non-stationary and non-linear. So for that we have to address that. How do we do that? By imposing an objective function. That objective function may be phase margin or gain margin or ISE or IAE or ITAE or overshoot or a less rise time or a 1 by 4 decay ratio. It depends on the user. Okay, so create an objective function which should follow that criteria. Then we have to use that mechanism. So for that we have four different technologies we have seen. One is scheduling, programmed or scheduled. Okay, next one is gain scheduling, and then next one is model reference adaptive controller, and then next one is STR, self-tuning regulator. So from this we can say that adaptive controller have been applied in chemical process. The range of their applicability has expanded with the introduction of digital computers, because the digital computers has to estimate the model. For process control, most of the adaptive controller systems require extensive computations for parameter estimation and optimal adjustment of the control parameters, which can be performed online only by digital computers. So since digital computers is ruling the world, so adaptive control is also applicable for this. Okay, that's all for today. Thanks for watching. Thank you.